All right, let's look at some of the questions from the fundamental theory of calculus problems that I posted. So here we have a graph of f of x, and we're told up in the top here that capital F of x is equal to the integral from 2 to, and it's kind of cut off here, so that's 2 to x of f of t dt. And we want to find f of 0, f of 2, 5, 7 minus 5, and f of 9. So we got a bunch of fundamental theorem things that we're going to work our way through here. So this one actually isn't too bad. We're just going to punch these things right in and use some of our rules for integrals. So let's start with a, and we're going to look for f of 0. Well, according to the equation then, that is from 2 to 0 of f of t dt. All right, so we're looking at this graph. Now it's 2 to 0. Whenever we get the top boundary smaller than the lower boundary, we're going to have to flip this over. And our rule says that if we flip this over from 0 to 2, we take the negative. We take the opposite of this. So this f of 0 is the area from 0 to 2. Okay, it's the area from 0 to 2, and then we're going to take the opposite of that. So this is just an area question. Now, how you find that area is completely up to you. You can solve it with the trapezoid, or you can split this up into the rectangle and the triangle. It really doesn't matter. If we just quickly look at the rectangle and the triangle, though, we're going to get 2 plus, this is base times height, so that's 2 times 2 divided by 2, so this is another 2, and we're going to get 4, but it's negative, so negative 4 is f of 0. Okay, maybe I'll get the next part in here as well. Let's go down here. Look at b, we want f of 2. Well, that would be from 2 to 2 of f of t dt. Well, now once again, the rule says if the two boundaries are the same, then that integral is just 0. All right, so there's the first two parts of that. Let's get rid of a few of these things then. You can always go back if you need to look at it again. Okay, so let's move on to part C here. C, we're looking at f of 5. So we're going to have from 2 to 5 of f of t dt. Okay, now one thing I want to point out here just before we get going too far, this is in t, and we're told here that it's x, and that really doesn't make any difference here now that we've substituted in this value here. This is really just the graph of f. That's what is important here. This is f, this is f. All right. Okay, let's get back to solving this. So now we want from 2 to 5, so we're looking at this area here. Now again, you could split this up into a rectangle and a triangle. How you find that area, completely up to you. Maybe just for this time, just to remember, I'm going to solve this with a trapezoid. So the trapezoid says I'm going to take the sum of the two heights divided by 2. So this is 1 and 3 divided by 2. And I'm going to multiply that by the width of our trapezoid, so that is 3. And if I go ahead and do that, I'm going to get 4 over 2, so this whole thing is 2 times 3, we get 6. Okay. All right, part D. Part D looks like it's going to be a little bigger, but we really want f of 7 minus f of 5. Well, this is nice because we just did that. We just did f of 5, so that is 6. So really what we have to do is find f of 7. So we're going to find f of 7 here. We're going from 2 to 7 of f of t dt. So we're going to go from 2 to 7. So we want 2 was all of this. We already know that is 6. And 7 is this part here. Well, now this part here is below the x-axis, so we got to remember when we do solve this, it's going to be a negative value. Okay, so we're going to take f of 7 becomes 6, and this triangle right here, base times height divided by 2, is actually equal to 3. So that becomes negative 3. So altogether then, negative 7 will be positive 3. 6 minus 3, so positive 3. So now our question, if we go back up here, we have f of 7, which is 3, minus f of 5, which is 6, and that will be negative 3. All right, let's keep going here. I'm going to eliminate a few things. All right, part E. Now for part E, we want f of 9. F of 9. So this is a big one here. We're going f of 9, so we need from 2 to 9. So we want the integral from 2 to 9 of f of x dx. And then we're going to take this part, which we've just kind of finished, and now this extra piece here. Well, we've done a lot of this already, right? This was 6. This little triangle down here we said was negative 3. So what we need is this piece right here. And I'm going to use my trapezoid again. So I'm going to add the 2 parallel sides. So I'm going to have a 2 plus a 3. And I need to divide that by 2. And then I'm going to multiply it by the height of our trapezoid, in this case 2. So we're going to cancel each of those. So this piece down here is 5, but it's below the axis, so that's negative 5. So altogether, if I put all of these pieces together, I'm going to get 6 minus 3 minus 5, and the whole thing becomes negative 2. All right, let's move on. All right, we want to figure out where does f have a maximum value and a minimum value. All right, so the first thing I'm going to do, let's bring that picture back here. So there's our graph. Where's this going to have a maximum value and a minimum value? All right, so let's look for maximum. Now, we're looking, just one more note here, we're trying to find where capital F has this maximum and minimum. So remember, we're going to get maximum and minimums when we get the derivative of f equal to 0. So this was our information. We were told f of x was 2 to x of f of t dt. Now we had a previous video, I hope you've looked at that, on the fundamental theorem. Basically this is nice fancy notation whenever we see this that says f prime of x is equal to f of x. So what they're telling us here is this graph is the derivative of capital F of x. So that is the derivative. So maximums and minimums occur when the derivative is equal to 0. So here's the derivative equal to 0. We're at 5. So let's go ahead and test 5. So I'm going to get my fundamental theorem here, or my little graph and number line. There's 5. So let's check when we're before 5. Everything before 5 here is all positive numbers. So my derivatives are positive. That means this is increasing. Capital F would just be increasing. After 5, the derivative is always negative. So we're decreasing. So we do get the maximum at x equal to 5. So we have f has a maximum at x, oops, I don't need that part, at x equal to 5. So how about the minimum value? Where does f have a minimum value? Well, I'm going to Just get rid of a bunch of this stuff. So we just said that the maximum occurs here, and that's where it switched from being positive to negative. But where does it have a minimum? Well, there's no other zero that we could test. Well, we do always have to remember that we need to test the endpoints. In this case, 9 over here. We got to test our endpoints. And the minimum is maybe occurring at one of those endpoints. Well, if we go back to part A, we saw that f of 0 was negative 4. It was negative 4. And f of 9 was negative 2. Now, after 0, we're actually getting bigger. They're all positive, so we're going up to that maximum value at 5. And then after 5, we're going down, and we get to negative 2. So it stands to reason that f has a minimum at x equal to 0. So test our endpoints, and it has a minimum at x equal to 0, simply from the first part that f of 0 was smaller than f of 9. All right, the last part of this question. What is the average value of f of x on 2 to 9? So from 2 to 9, what is the average value of f of x? So let's just recall, first of all, that the average of a function is 1 over b minus a times the integral from a to b of that function. That is our formula for the average value of a function. So if we want the average of f of x from 2 to 9, that becomes 9 minus 2 from 2 to 9 of f of x dx. Well, this part here is f of 9. We've done that earlier in the question. That was f of 9. That's how we found that in part A. So this whole thing now becomes 1 over 7 times f of 9. And f of 9 was negative 2. So our average value of f of x, so f of x, we'll say average, was equal to negative 2 over 7. And we're all done with number 16. All right, let's try the next question, number 17. So once again, we're told g of x is the integral from 0 to x of f of t, and then we have the graph of f. So just a little note, and I encourage you to write on the page. Now, it'll be a little harder now, but basically they're telling us this is g prime. Now, we want to know at what values of x do the local maximum and local minimums of g occur. So when do we get maximums and minimums? So again, we're trying to find when does g prime equal 0? When does the graph equal 0? Well, we have a few of them. We got 1, 2, 3, 4, 5, 6. So there's our 6 right there. Now, we've always sketched it out. I'm giving you a little different way here, and then we'll justify it. So let's look at some maximums. So first of all, I'm going to get rid of this so I have a little bit more room. So let's look at our maximums. We'll say g has local maximums at, well, our choices are 0, 1, 3, 5, 7, and 9, but we get a local max when our graph goes from positive to negative. So if we're going from positive to negative, we get a local maximum. Again, just graphically, that means our derivative went from positive to negative. It was going up, and then the original was going down. So this is what we've done a lot of times. Now we're just going to shorten that up and saying we're going to be at 1 because we went from positive to negative. Now again, at 5, because the graph goes from positive to negative. And that's all we know. We can't say 9 because it's positive here, but now we're done. We don't know if this graph, turns back up or something else is happening here. So we can't say it actually has a local max at 9. Okay, so we're going to say it has local max at x equal to 1 and 5, and we'll say because we got to justify our answer because the graph of G prime goes from positive to negative. And that's how we would justify that. Now we can do the same thing if we look for minimums. So when we look for minimums, if we go from negative to positive, we're going to get a minimum. Again, just looking at what we've done before, anytime we've gone from negative, where the original was going down, to positive in our prime, we're going up, that was a minimum value. So negative to positive, negative to positive. Now, just like 9 before, we can't tell what was happening before 0, so we can't say that that's a minimum. So I'm going to move this up, and we'll answer that last question. Say G has local min at x equal to, we said 3 and 7. Okay, 3 and 7. Let's just bring that down. 3 and 7. And we'll justify it by saying because the graph of G prime goes from negative to positive. And that's enough for our justification. But write that down. Make sure you justify something in there. All right, let's move on. Okay, so here's the second part. Where does G attain its absolute maximum value? Where do we get the absolute maximum value? All right, well, looking at the graphs here now, I'm just going to add some numbers in here. Now, we don't have numbers, but we can estimate a little bit, and it's not really estimating. We're just going to put in something. So this looks like it's a little positive here. So let's call that, just to make it easy, let's say that's 1. This area here, clearly bigger than this one, so we'll say that's 2, but it's below, so that's negative. This area is getting bigger, and each area is getting bigger, that's below the axis, and then this one is 5. So now, if we think of this really as an object that is moving to the right, and then to the left, and then to the right, and left, and right, and left, we can see that if we start here, after 1, we're 1 away, then we turned around, and we moved 2 back this way. Then we turned around again here. We turned around and we moved to 3. And then we turned around and moved 4. And then we turned around and moved 5. So where do we actually get an absolute maximum value? Well, we get the furthest away really at the end at time equal to 9. So we're going to say at x equal to 9 is when we have an absolute maximum. All right, part C. On what approximate intervals is G concave down? When is it concave down? Well, concave down occurs when the second derivative is equal to 0. That's when we get our point of inflections, and that's when we can determine whether or not something is concave up or concave down. So again, I like doing kind of our 3-level chart. So I'm going to make my 3-level chart here. This will be the second derivative, that is the first derivative, and that is my original. And I'm going to lay out some things. The endpoints here at 0, I'm going to make it a little longer so we're not cramped here. And I'm going to put 9. And then really in between, we're going to have 1, what should we do? 2, 3, 4, 5, 6. And you can see I'm going to have to make this a little bit longer still. So I'm going to go 7, 8, 9. We'll extend that out. All right, now let's just take a look at what is happening to our function. Well, from 0 to 1, well, it's actually from 0 to a half, it looks like we're going up. And that was actually at a half. And then from a half all the way to 2, from this half all the way to 2, we're going down. From 2 all the way to 4, we're going up. From 4 to 6, we're going down. And from 6 to 8, we're going up. And then from 8 to 9, that little piece there, we are going down again. So we can just map this out. Now that tells us that in this area here, if we're going up, that means my derivative of g prime, which is g double prime, is positive, and we would be concave up. Here we're concave down. From 2 to 4, this is going up, so its derivative is positive, and that means we're concave up. Minus to 6, concave down. So we're just kind of filling in our chart here. From 6 to 8, going up, so its derivative is positive, we're concave up. And from 8 to 9, its derivative is negative, that would be concave down. So we can see when are we concave down. It's just asking for the intervals. So when are we concave down? We can say we're concave down here, looks like when x is greater than 0.5 to 2, less than 2, when x is greater than 4 and less than 6, and finally when x is greater than 8 but less than 9. So there's our 3 intervals where our function is concave down. Now we have the last little bit here where we're asked to sketch the graph of g. Remember, this is g prime. So what would g look like? Well, we had a lot of information in that last little graph. Okay, so I'm going to go pick that up and then paste it here. So this is what we had in that last little chart there. So we got a lot of information here. So now if I want to sketch this one, let's sketch this. And I'm going to put in a few of our numbers here, and we'll do the same thing. We'll say there's 2, 4, there's 6, there's 8, and there's 9 out here at the end. Okay. All right, now let's analyze our chart and our graph together. And we can see from 0 to 0.5, our derivative is positive. That means we're going up and we're concave up. So from 0 to 0.5, we're going up and we're concave up. Now, from 0.5 to 1, we're still going up. We're still positive numbers, so we're still going up. But at 0.5 was a point of inflection. And we can see now that the graph is decreasing. So the graph is decreasing. That means we're concave down. So we're from 0.5 to 1, we're concave down, but we're still in the positive numbers. Now, at 1, we go to negative numbers. So from 1 to 3, these are all negative numbers. So our graph has to be going down at this point. And 2, we said, was a point of inflection. So we're still concave down all the way to 2, Now from 2 to 3, we're going down, but we've changed to concave up. So we're concave up until we get to 3. Now 3, we're still concave up, but now at 3, our graph G prime is positive, so we're increasing from 3 all the way to 5, we're going up, and at 4, we reach another point of inflection. So we now go to concave down, but we're still increasing until we get to 5. 5, if we go way back, was one of our local maximum values. And then this pattern kind of continues, right? From 5 to 6, G prime is decreasing, so it's concave down, but at 5 we actually change from being positive to being negative, so we're concave down, and then after 6 here you can see we're concave up, and then we get to 7 was one of our local minimums. And I'm just going to kind of finish this off. We're going to get something that looks about like that. So you just want to follow the graphs that you made, and you may want to redraw this to see both whether G prime is increasing and positive numbers, increasing and negative numbers, and so on. So this is increasing positive, this is increasing and negative. So we are increasing, but we're negative values, right? They're going down here. So this is what our graph looks like. That was probably the tough part of this particular question. All right, I'll keep posting the answers to these.